Hey y'all, today we're going to take a look at coupled reactions. We're going to tell you what they are, how we can use them, and how we can actually couple reactions together. So let's go ahead and get started. A quick recap of delta G. We've been talking about E values during this unit, but remember that they're always connected back to delta G. A positive E value is going to have a negative delta G value. That means it's spontaneous, it's thermodynamically favorable. So a reaction that has a positive E value is going to happen spontaneously. A reaction, therefore, with a positive E value that has a delta G that is negative is going to spontaneously occur. What that means is that it'll happen without us adding any further energy into the system. But that being said, not every reaction is spontaneous. Some reactions are going to have negative E values, which means they'll have positive delta G values, which means that they are not spontaneous. They're not thermodynamically favorable. What if we wanted to perform one of those reactions that's not favorable? How would we do it? Well, the answer, we can use a coupling of reactions to achieve that end. So a definition here, coupled reactions are when you take two or more reactions, you put them together into essentially one linked system, and in doing so, you allow for the thermodynamically favorable reaction to essentially drive the unfavorable process to happen. So through this coupling, we create an entire system which overall is favorable, has a negative delta G or a positive E, but one of those steps, the one that we perhaps wanted to occur, wouldn't have by itself. Now, in a way, coupling reactions is a little bit like Hess's law, where we take multiple different reactions and we add them together stoichiometrically to get a product that we're looking for. In this case, the Hess's law is with E values or delta G values. And so when we're coupling reactions, we can actually approach them in a sense the same way we would approach Hess's law questions back in thermochemistry. One of the most common examples of coupled reactions comes actually out of biology, metabolism. Our body's metabolism is actually an important coupling of many reactions. The most common example here is going to be the process by which we create sucrose out of glucose and fructose. And in doing so, we're going to utilize the process of ATP turning into ADP to drive that process. See, the formation of sucrose is unfavorable, but we need it. We need those macromolecules. So in order to do that, we have a system in place where we essentially, through our metabolism, are going to turn ATP into ADP. That process, which has a negative delta G, a positive E, is going to then essentially drive the unfavorable process of the sucrose formation to occurring. So again, thinking of this like Hess's law, what we're going to do is we're going to take the delta G of the first process, that formation of sucrose. We're going to take the delta G of the ATP to ADP process. We're going to add them together. And you can see in the end, we end up with a delta G that is negative, which means it's a spontaneous process. Beyond biological systems, one of the ways that we use coupling reactions is oftentimes with the production or refinement of ore. Ore is metals that haven't been purified yet, and we need to refine that ore to create a metal that we then can use. So if we look at zinc ore, for example, this would be zinc that has other stuff in it, like zinc sulfide, for example. We need to get the zinc isolated by itself. We want to purify the zinc. In order to do that, we need to drive out that sulfur. The sulfur is not easy to drive out, though. When we look at this, in the end, that sulfur being driven out has a very positive delta G value, a very negative E value. So in order for this to happen, we need to apply a secondary process. In this case, it would be the fact that sulfur and oxygen together are going to have a favorable process to form sulfur dioxide. The delta G of that process is very negative, so it is a spontaneous process. And as you can see, if we pair these two processes together, the total delta G value will therefore be negative. So in this process of being able to purify zinc ore to pure zinc, all we have to do is pair it with oxygen gas. And when we do the Hess's law type problem, what we see is that we will then have pure zinc as a result. And that will be a spontaneous process. Because this is Hess's law, one thing to be aware of is that we can also look at the actual steps of the equation too. See how the sulfur cancels on both sides of this equation? So in a sense, what we're seeing in the net reaction is that it's zinc ore and oxygen to get to that zinc and sulfur dioxide in the end. As I've said at the beginning of this video and throughout the video, I'm using delta G and E values because of the fact that they're connected. Delta G is equal to negative NFE. What that means is that as delta G becomes more negative, the E value becomes more positive. As the E value becomes more negative, the delta G value becomes more positive. Remember, a positive E is spontaneous, thermodynamically favorable. A negative delta G is spontaneous, thermodynamically favorable. And as a recap, we use coupled reactions to bring multiple different processes together into a single system that is overall thermodynamically favorable. So that wraps up today's video. Pretty quick one. Today we learned about coupled reactions. I gave you a definition for coupled reactions and gave you a couple of examples where you would use coupled reactions. Remember, coupled reactions are pairing multiple reactions together to be able to drive a process that by itself would not have been spontaneous or thermodynamically favorable. We see these in biological systems all over the place because evolutionarily they are very favorable. We also see these in a lot of industrial processes. We also connected this idea to Hess's law. And in doing so, I reminded you the fact that we can add together these delta G values or these E values to get an overall E of the process or a delta G of the process. Just like in Hess's law, all of those same things on opposite sides will cancel. If they're on the same side, then they'll add together. And so we can get a net process reaction out of these multiple elementary processes going on. Today's video was written, produced, directed, and edited by Isaac Chan and Jasper Xu. Thank you all for watching it. I hope you enjoyed it, and I'll see you in the next one.